Hi folks, DD Solar here. This video is a double feature. It's going to cover basic electronics knowledge useful for DIY solar power enthusiasts in troubleshooting things like DC to AC inverters, lithium-ion BMSs, and so forth. If there's time, I may cover some other topics as well. It's also a review of this digital multimeter and oscilloscope made by Gochifix. Please note this multimeter was provided to me by Banggood for review, and I don't make any income from the sales. I will be giving you my first impressions and straightforward opinions as a long-time user of digital multimeters. Before starting the video, I'm just going to take a quick look at the box. Here's the box it comes in. It says it's an oscilloscope, a multimeter, and a waveform generator, so 3 in 1. And it's also got auto ranging and a really nice screen. Now on the left-hand side of the screen, right over here, you can actually see the multimeter, and that's in real time. That's recorded from a separate camera. Inside the box is some accessories. You get a nice carrying case. You get a pretty decent manual. You get a USB charging cable, and you get the multimeter probes. You also get a quick start guide. So I'm going to take a quick look at those. I do appreciate the effort they went to make this quick start guide. This will just kind of get you started. You can read about the basic functions and the keys, and I think this is very nice that they put this in here, so I don't have a problem with that. This multimeter, when I first got it, I was already dreading the batteries and thinking that I need to find some batteries for it. But when I got it out of the box and turned it on, it just came right on, and I discovered that it's USB charged. It has a lithium-ion cell inside to power it, so you use this cable here and you can just charge it from USB. So I think that's pretty good. And the manual is actually quite decent. It's a pretty detailed guide, and it shows you all the different ranges and all the different things that it can do, and I'll certainly be taking a look at that later. So far, so good. It has a set of function keys along the top. It's got a typical rotary dial. It is considered a smart multimeter, but it also has this nice rotary dial. I do appreciate that. I really prefer a multimeter with a rotary dial because that's what I've used for many, many years, and yet it has all the smart functionality as well. It has a rubber overmolded case, which is nice, and I really appreciate the kickstand, which pops out of the back. As you know, multimeters are always kind of aggravating to keep at an angle, which is the best for viewing them, and this kickstand solves the problem. It also seems to have a detent, so it has 2 different angles. Okay, so I'm going to go ahead and power this multimeter on and start using it, and go ahead and proceed with the video. Alright, let's get right into learning some basic skills for solar power enthusiasts using multimeters and understanding different electronic and electrical components. By the way, I have another video in this series about multimeters, and I highly recommend watching it. The link is in the description. I'm going to power the meter on, and to do that you simply turn the rotary dial. It lights up. It has a very nice light inside the dial here, which is really interesting looking. I must say, it's quite impressive. The appearance of this meter is quite impressive. As you can see, the screen is decent looking, very bright and easy to read. There's a backlight setting right here. As you can see, it defaults to 600 volts, auto, and it does have a millivolt sign right there, so it's very sensitive and it's measuring only millivolts right now. Auto simply means that it will try to pick the best range for you when you start measuring voltage. Now, a multimeter is one of the most basic and critical instruments for a DIY solar power enthusiast, and it can do so many different things. This meter also packs in a digital oscilloscope and a tone generator, and I'll address that later in the video. You probably will encounter at some point in your existence a lithium-ion battery pack. Here is just an example for this review and this demonstration. This is a 3S battery pack using lithium-ion 18650 cells. This particular battery pack came out of a solar generator, which I've had and I actually worked on. And you can see it has various connections. And as a solar power enthusiast, you might come across something like this and you want to know, is it working? Is it worth anything? Is there something wrong with it? If so, what's wrong with it? And, maybe what's the voltage or how much power is left in it, things like that. Actually, there's a lot of things you could check on this board and on this battery pack just with a multimeter. You don't need anything else. This video is basically going to function as a primer or an introduction to help people increase their skills and probably their safety factor too in using a multimeter with solar power. So we're going to use this battery pack as an example for part of this video. The probes that come with this meter are pretty decent, and they are quite sharp as well. They have these shrouds that go over the tips so that you don't accidentally short something out. Let's go ahead and take a look at this thing and see if the multimeter can help us make any determination about this battery pack, whether it's any good. For starters, I'm going to take my multimeter probes, I'm going to place them on negative and positive. and you can see that we're getting 10.3 volts on the multimeter, and so this battery pack is certainly not dead. It may not be in the best of shape, but it's not dead. Now, battery packs like this typically have some kind of a BMS or a balancing board or balancing circuit located either on the battery or externally to it. It's worth pointing out that you may need to measure individual cells in a battery pack like this to determine if any of them are dead. Now, I'm going to go ahead and warn you that when doing any kind of work like this, one of the number one mistakes people make is they use their multimeter probes and they accidentally slip and they short something out. And when you're dealing with a battery like this, if you short out this probe across a battery terminal, a lot of current is going to flow, and so you've got to be very careful where you stick these metal probes. And if you're not sure, don't touch them to anything until you've identified the test point that you're using. And that's why these shrouds are so useful, because now you have more metal exposed. But if I put the shroud on, there's a lot less metal exposed, and it's a lot less likely that I'll make a mistake and short something out. Let's just make a quick measurement of the individual cells of this battery pack. It's a 3S system. Sometimes it's hard to identify, but generally speaking, if you're going to take a measurement of the individual cells on a battery pack like this, you want to find the battery main positive and negative as well as the midpoints on that battery pack. And that's where the cells attach to each other in series. On this battery pack, you can see there's a B- here, and it's obvious that there's a high current terminal here. There's 3 connections. So I'm going to take my negative probe and place it right there. And right over here, you can actually see there's a 3.7 volt marking right here on the BMS board. And that's the first cell, so I'm just going to measure there. As you can see, 3.438 volts. Now over here where my finger's pointing, there's a 7.4 volt marking, and that's the next cell over. So to measure that cell, what I'm going to do is I'm going to move my multimeter probe over to 3.7 volts, and then I'm going to touch the 7.4 volts. And you'll see that cell is running at about 3.4 volts. So it certainly isn't full, but it's not completely flat dead either. Now to complete the measurement of the third cell, I'm going to attach my other multimeter probe to the 7.4 volt mark, and I'm going to measure the final terminal in the battery pack. You can see I'm again running at about 3.45 volts. And that's how you use a multimeter to check the cells on a lithium-ion battery pack that uses a BMS like this. Sometimes you can't really get to the cells themselves, and you're forced to use whatever connections are available on the BMS itself. Okay, so I've only been using this meter for a relatively short time, less than an hour, and I'm pretty impressed with the screen, and also the readout on the display seems to be quite responsive and it updates pretty quick. So no problem there. Now, as a solar power enthusiast, no doubt at some point in time you've encountered diodes. Diodes are usually placed inside of solar panels, and they're in the junction box, and they're used as bypass diodes. There's also blocking diodes, which you may encounter at some point in time. But diodes are one of the most common components found in electronic circuits everywhere, and in solar power, there's almost no way you're not going to see a diode sooner or later, either in a solar panel or in some circuit board somewhere. So knowing what a diode is and how it works in a basic level, and also knowing how to test them, could actually be very important, and it could even save you money. Now, a diode is a semiconductor device that only passes voltage generally in one direction. That's the general idea. It also has a voltage drop, so if you pass voltage across it, it's going to drop a certain amount of voltage. The amount of voltage may vary, but more or less it's going to be around a half a volt. It might be as little as 0.2 of a volt. In any case, you can test a diode using a multimeter. If you have a diode in the back of a solar panel in a junction box and you believe it has failed, it's important to check that diode to see if there's anything wrong with it. So I'm going to go ahead and use the Gochifix meter here to check a diode. These are brand new diodes. They're in a bag, so obviously they must be working. But I will go ahead and tell you what to expect if a diode is not working. In order to check a diode properly using a multimeter, generally speaking, you're going to want to go to the diode check or continuity mode on the meter. On the Gochifix, let's go ahead and take a look at the dial. If you look there on the meter, it actually says diode, ohms, and continuity, or there's a tone icon. So we're going to go ahead and select that. Alright, so I've selected diode mode. Now, since the meter has defaulted to resistance, it's better to go into the specific diode mode which is built into that meter. And in order to do that, you have to press F3. And then that's for the SEL function, or select, and it goes into diode mode. Now we're in diode, auto and diode. You can see that it says .OL on the screen. Basically means there's nothing there. It's open circuit or overload, and it has a voltage icon. Now, the way you test a diode, or the way a multimeter tests a diode, is it actually will pass a voltage across the diode, and it will see how much of that drops, and it can recognize whether it's a diode, or at least the user of the multimeter can, even if the multimeter itself cannot. How do you test a diode to see if it's working? Let's go ahead and do that now. So I've zoomed in on the diode, and I'm going to take the multimeter probes, and you can see the diode has a stripe on it. if you want to, you can just go ahead and connect to the diode on either side and not worry about the polarity and then swap it out. You have a 50-50 chance of getting it right. In my case, I know that I want to connect the red or positive probe to this side of the diode and the negative to this side. The meter is now showing a 0.527 volt drop. For a diode like this, a silicon diode, you want to see about 0.5 of a volt in drop, and that's exactly what's showing up on the display. For other types of diodes like Schottky diodes, there might be less voltage drop. But the point is, it is passing voltage and it's dropping a little bit of it. Now what you don't want to see is, you don't want to see, when you touch these probes, you don't want to see like a short circuit. So I'll give you an example. If I take the probe and I place it here and I place the other probe here, you can see it says 0.002 volt. Well, basically it's saying 0 volts. Essentially this is a short circuit. You don't want to see a diode reading like that because if you take a diode out of your solar panel and it's reading that, it probably isn't working anymore. Now if you turn the diode around, don't change polarity, just turn the diode around. It's just the other way of doing it. Or you can turn the multimeter leads around. You're going to get nothing. Ideally, when you measure the diode backwards like this, you're not going to see anything on the meter when it's in diode mode. Now if you do see something there, and it's not very much, it's a low readout, it's probably a bad diode, it's probably burned out. Now, diodes can fail in different ways. They may go open circuit, where they basically don't conduct regardless, no matter how you connect them, or they may conduct everything no matter what direction it's attached. Either way, it's a failure. So let's turn the diode around and put it back like it was, and again, look at the screen. That's what you want to see when a diode is, a silicon rectifier diode like this is working. You get about a half a volt of drop. Here's some other diodes that I have. And just for kicks, let's go ahead and measure one of these and see what they say. And as you can see, I'm getting about 0.56 really of a volt. It's pretty much the same. Now all diodes are not perfectly identical, and you're bound to get a slightly different reading from diode to diode, and that's nothing to be concerned about. These components are made by the billions, and they're just not all going to be the same. That's the way it is with mass production, so it's nothing to be concerned about. If you need to check 10 solar panels with 10 diodes, as long as they're all within 5% of each other, it's nothing to be concerned about. What if you have a DC to AC inverter connected to the battery and you suspect that it's not working so well, and you want to give it some basic checks? Well, believe it or not, that's not too difficult to do, especially with this multimeter. It allows you to do quite a bit more than you might think. The most basic check would be to see if the inverter is on, and this inverter is on. And it's hard to see, but the power light is on. It's putting out AC power. So the first thing I'd like to see is, what is the output at the terminals? And that plug is actually right here on the side. What is the output at the terminals? Is it actually putting out 120 volts AC? The first thing you want to do is, I'm going to go ahead and take the meter and I'm going to put it over here. The first thing you want to do with any multimeter before you take a voltage measurement is make sure you're not plugged into the 10 amp range, which is right here. And make sure you're plugged into common and voltage, which I am. Because if you plug it in here and you try to measure the AC outlet on an inverter or on the wall in a house, it will just blow up the fuse and it could damage the meter. But of course I'm not plugged into 10 amps, and so I'm going to go ahead and make the measurement. Now in order to measure the voltage with this meter, I need to go to the voltage DC range. And as you can see, there is a voltage range. If I turn the dial this way, it actually has a V, and then it has a flat line and a curved line. And the flat line and the curved line essentially is saying DC and AC voltage. And that's just a symbol, and it's kind of like a short, compact way to tell you it's both DC and AC. And voltage range, it's on auto, and you can see that it's also on DC. Now I want to measure AC, not DC. So I need to press select, which is F3. And now it's gone into AC mode. It's still on auto ranging, and that means that the meter should be able to pick up the correct range, whether it's 100 volts or really low voltage or really high voltage, automatically. So I shouldn't have to do anything else. Now what I'm going to do is I'm going to take the shrouds off the probes on my meter, being careful not to stick myself with them. And this is where you should really be careful. Generally speaking, if you're going to stick anything into the outlet of an AC inverter or any AC source, you're going to want to go ahead and use one hand. And that takes some getting used to. I generally don't use both hands. Now what I'm going to do is basically take these probes with one hand and I'm going to put them right into the outlet. Polarity doesn't matter because I'm measuring AC, so we're going to go ahead and see what this inverter is putting out. And the meter is now beeping and telling me that we have high voltage. It's AC, 120 volts. Very interesting how a little icon lit up. You can see right there, there's an icon, a little lightning bolt. And they're very smart to warn you, because if you stick your finger on those probes, right here where I'm pointing, let's just say you're going to feel it. I won't go into details after that. You can see the inverter's putting out about 120 volts AC, and that's pretty good. However, that's not a whole lot of information. What if I want to see how the inverter is actually performing. What about the waveform? Just so happens this meter here has also a digital oscilloscope, and we should be able to see the waveform on a screen and see if there's any problem with it. So let's go ahead and check it now. In order to do this kind of measurement, we need to go into oscilloscope mode. In order to tell this meter to use the oscilloscope function, we take the auto key and just hold it down for 2 seconds. And you hear a relay click inside the device, and it goes into oscilloscope mode. Now it's really nice to have this capability built into a multimeter without having to go get another instrument or without having to use up extra space on your workbench. I just pressed auto for 2 seconds. I went right into oscilloscope mode. I'm not touching anything else, and I'm just going to take the probes and stick them right in the inverter yet again. And it's hard to get them to make contact, but that is representing a sinusoidal waveform on the screen, and that's actually the AC inverter doing what it's supposed to do. And I didn't have to do anything else. I just stuck the probes in there. I didn't make any adjustments. It's telling me that we have about 59.9 hertz or 60 hertz. And actually this is really nice because when there's a problem with an inverter, a lot of times simply looking at the waveform will tell you there's something wrong. And in fact, it's possible that if there's something wrong with the inverter, you'll see a lot of noise, you'll see large spikes, and there could be actually a problem. It could damage your appliances. So what I'm seeing here is almost a perfect waveform, and there's nothing to complain about. It would be really nice to see a closer and more detailed view of this waveform. As it stands now, it's kind of a zoomed out view. If you look in the lower left hand corner of the screen, you can actually see the word time. I'm going to press F1, and this is all relatively self-explanatory, and I'm going to decrease the time base. And when I do that, you can actually zoom into the waveform and have a pretty close look at it. And again, the waveform looks very solid. I don't see any problem with this inverter. And if you ever have a problem with an inverter, this would be a really quick way to see at a glance if it's really working the way it should. Just to be clear, there's a teeny tiny bit of variation on the screen, and that's simply because an oscilloscope is extremely sensitive, and even the slightest bit of noise can show up on the screen. That's really nothing to be concerned about. Now, I'm going to take the probes out, and I want to escape oscilloscope mode. How do I get out of it? The quickest way is simply just to go to off and turn it back on. I don't have a problem with that. So now we're back in the default DC voltage range, and we can go on from there. Now one of these days a solar power enthusiast is going to want to answer the question, is the wire broken or not? In other words, is a piece of wire or a length of cable actually connected to anything, or is it broken or damaged? And one of the most simple ways you can check that is with what's called a continuity check. The continuity check is built into the same place as resistance and diode check. Diode check mode, resistance mode, and also continuity mode. It's 3 modes in one. You can see I've switched it to that location there. In order to enter continuity mode, I have to press F3, which is related to select on the screen. I'm going to hit that once. It goes into diode mode, which we already know about. And then you hit it again, it goes into continuity. And you can see that it says open circuit. There's a little icon of a speaker here on the display. That means you're going to get a beep. So let's test the continuity mode real quick by just touching the probes together. You can see that whenever I touch the probes, instantly there's a beeping sound. And that indicates continuity. So let's just pretend that these alligator clips here are a cable running underground. Maybe it's a solar panel feed, and we're not sure if there's a broken wire, but we can go ahead and check one side of the conductors, positive or negative, to see if there's a break in the cable. So I'll just touch the probes, and you'll see there's a continuous tone. And that means that basically there's a good connection there. It also displays the resistance in ohms, which is essentially nothing. There's almost no resistance at all. But basically, if I am testing a conductor, and let's just say, it's 10 feet or 5 feet, it's not a super long piece of cable, and I hear this tone, what that's telling me is basically there's not a break in the cable. Now, of course, there are other circumstances, there could be something weird going on, but generally speaking, it means you have a good connection. There's also a resistance readout on the display. But in reality, the test leads themselves have a small amount of resistance in them, and so really what it's saying is there's no resistance. This connection here is perfectly fine, there's nothing wrong with it. Here's a small amount of feedback for the meter manufacturer. When in diode mode, which is you have to actually manually go into it, so I'm going to go back into diode mode. When you test a diode, you get a readout on the display, and that's it. What you really want to hear when you test a diode is a beep, and it would be a short beep for, say, a low voltage diode, a germanium diode, and maybe a different beep for a silicon diode that's dropping a half a volt. Really, that's just a small bit of feedback I have for the manufacturer of the meter. If they could just rewrite the firmware a little bit to have a beep for testing diodes, that would be amazing. And the continuity check is, as far as I can tell, the only time this meter beeps. It's really nitpicking at this point. The meter so far has done everything I asked it to do, and I really can't complain. But that's that. Now, in solar power and off-grid systems, a lot of times you'll come across an inverter that has stopped working, and it isn't really clear what's wrong with it or what happened. What are two of the quickest things you can check on a inverter, whether it's a pure sine wave inverter like this sample here, or even a modified square wave inverter? It really doesn't matter. What are the two quickest things you can check using a multimeter to see if certain failures have occurred? Well, there are actually two really common failures on inverters. And basically, an inverter like this would have an input stage, and then it would have an output stage. And a lot of times the input stage, which would be where your batteries connect here, that would actually short out. Or something would happen on the input side, because the input side is handling a lot of current, whereas the output side is handling less current. Let's go ahead and use a multimeter to check this inverter and see if there's any problem with the input stage, and then I'll explain what you should look for when doing that. What I've done is I've removed these bolts off of the battery terminals so I can access them with the multimeter. I've set my multimeter to the auto resistance range in ohms, so you want to measure resistance here. And what I'm going to basically do is I'm just going to probe positive and negative with my ohm meter. Okay, so what you're seeing here is the capacitors on the input are charging up, but you're seeing, hundreds of ohms. That's 3 kiloohms, so that's thousands of ohms now. And you can see it slowly going up there. Notice the K and the ohm signs on the right-hand side. Now it's up to 44 k ohms, so 44,000 ohms. That's a lot of ohms, and that number is going to keep going up. What does that mean? Well, the first thing that we can determine here is it is not a short circuit. What would a short circuit look like on an inverter like this? Well, it would look something like this. If I just probe one side of the terminal, you can see all the zeros, and basically it's saying, 0.4 of an ohm, 0.3. Really, it's saying it's 0. But when I probe this inverter, I actually get something more like this. You can see 469.9 kiloohms. That's thousands of ohms, so 470,000 ohms. That cannot possibly be a short circuit. But you can also determine one more piece of information, and that is, it's not a short circuit, but it's also not an open circuit. So this inverter most likely has the fuses intact. And most likely what we're seeing when we measure it is we're seeing the input capacitors, which are across the input, and we're seeing the input resistance of the inverter is very, very high. And so that means there's really nothing wrong with the input of the inverter. It's not short circuit. And what are the different things that you might see if you do a test like this? Well, one would be an open circuit. If you probe the inverter, just like I did here, like I showed you, and you don't see anything on the meter. Now, I'm not actually touching the probes to the other terminal, but let's just pretend that I did, and you saw OL on the meter like that. What is that telling you? What that's telling you is there's an open circuit on the input of the inverter. What does that tell us about the inverter if it just says open circuit on the meter when I probe these two connections? What it's telling you is that something has gone wrong inside the inverter because it should not be open circuit. More than likely what's happened at the very least is the fuses, which are often placed inside these types of inverters, has actually been blown. Now, not all inverters are built the same. They're all different. This is just an example of one. And they may have fuses inside that you can't see. Some inverters will have the fuses on the back. This particular model doesn't. This particular model, you have to open it to see any fuses that are inside of it. Some inverters have the fuses soldered down to the circuit board inside. Those are a real pain. Some of them have sockets, and you can just replace the fuses. However, before you do that, if the fuse blew, then something went wrong, and replacing the fuses probably isn't going to fix it. Okay, to summarize, if you're going to check the input stage of the inverter, inverters have an input stage, that's where your battery connects, and they have an output stage, and that's where you plug in your AC appliances, high voltage. Let's summarize the input stage. If I check the input of an inverter, DC to AC inverter with a multimeter, and it says open circuit, you're going to have to open the inverter to look inside. If the fuses are not external, more than likely you're going to have to open the inverter. If you replace the fuses because of an open circuit condition, very, very likely what's going to happen when you power the inverter up, it's just going to blow the fuses again. If you probe the input of the inverter and you see an actual measurement, what you're looking for is you want to see hundreds of ohms, you want to see thousands of ohms, maybe hundreds of thousands of ohms, and you also want to see that reading starting to climb upwards because that would just indicate you're charging the capacitors on the input, and that's a pretty normal reading. That's nothing to be concerned about. It means the input is probably okay. It's probably not shorted. It's certainly not a guarantee of anything, but it does give you some information without actually opening the inverter and without spending a whole lot of time. If you probe the inverter and you see a readout that looks like this, I'm going to do it again. You can see it counting down and going down the ranges, and it goes into basically 0 ohms. Essentially, it's saying 0.3 of an ohm, but in actual fact, it's probably pretty much 0 ohms. It's just showing you the wires that are connecting the test probes. Essentially, that's 0 ohms, and it's a short circuit. If you see that on an inverter, first of all, do not try to reconnect it to your solar power system. Don't reconnect it to your battery banks, or reset the circuit breaker, or replace the fuses, because a short circuit means that the inverter requires repair. There's no way around it. It's going to require service. Probably a transistor or something on the input is shorted out, and it's all gone wrong, and it's going to need to be replaced. Using a digital multimeter, you can find that answer, whether there's a short circuit on the input, in just a few minutes. It doesn't take much effort at all, and you don't have to hire anybody or pay anybody to make that determination. So it's very handy to know how to do these things. Now let's take a look at the output side of the inverter. The output side, or output stage, that's where the AC voltage comes out, the high voltage, as a sine wave. How do we measure that? I've turned the inverter over where we can look at the front of it, and you can see this particular model has 2 outlets on the front. The first thing you want to do is make sure the inverter is powered down and disconnected from the battery before you do this test. Treat it very much like you would if you're measuring the wall outlets in a typical house. You really don't want to mess around. In general, it should be safe to do this test. You're going to want to be on ohms range yet again, so I've got the meter on ohms or resistance. And what I'm going to do is, first is I'm going to identify live and neutral. So live and neutral are these 2 flat vertical slots. And then you have ground, and that's the one below it that's kind of in the middle. Now, this is a North American style inverter, 120 volt. If you're in Europe or in another country, there's going to be a different looking outlet. But it doesn't matter because the process will be essentially the same. And I'm just going to take the probes and I'm going to put them right in live and neutral, or neutral and live. Polarity does not matter. You can see right away I have a pretty high reading. It's jumping around some because I'm not making good contact, but it's hundreds and hundreds of ohms. Notice now that I'm measuring between these 2 terminals here. This is the live and neutral. And this is the reason why one is a little bit bigger than the other, because there's supposed to be a difference between them. But on an inverter, it's a little different because we're not actually tied usually into the wiring inside the home or the cabin or wherever you're running the inverter. It's just kind of floating. There are different kinds of inverters, and there is a possibility that some of them may actually use this terminal here to present the voltage. I don't think this inverter is that kind, but I'm going to measure it anyway, just to be safe. I'm going to take one probe and I'm going to place it in the ground, this side here. Then I'm going to measure to the other side. And there really doesn't appear to be any connectivity here. And I really don't want to see any connectivity here between ground and live or neutral. And I don't. In this particular inverter, I'd be very surprised to find any connectivity between the 2. And just to be clear, in many cases on many inverters, this terminal here is literally floating. It's not connected to anything. But you still need to check resistance between all these terminals, because if there happen to be some kind of a short circuit or a failure here, you need to know that. Just to be clear here, there are some inverters that I have never actually seen myself, but they must exist, that will present the voltage between ground and these 2 terminals here. So you would get voltage from here to here and voltage from here to here. Those inverters, I've never personally seen one, but I've heard they do exist, but just so you're aware of that. On the output stage of an inverter, we have pretty much the same story. If you find a short circuit, I'm going to demonstrate that. If you put your probes here in these 2 places, and you get a readout on the meter that looks like what I'm showing you now, as you can see I'm crossing the probes. Once again, you have a problem. You should not try to power the inverter on. It's just going to blow the fuse probably, and worst of all, you may cause more damage to the inverter than it already has. Typically, when there's a short on the output stage, you're going to have to replace the transistors on the output side. And if you have a really cheap inverter, that may not be worth the effort. It's up to you, but just so you know. Once again, on the output stage, there are 3 conditions you might have. You might have a short circuit, which means you must make a repair. You may see an open circuit. If you have an open circuit on the input side of this inverter, that will be a cause for concern. And it might be that you need to open the inverter to see if maybe the wires have fallen off these plugs. For example, these outlets here sometimes have really bad connections behind them. You'd be surprised what I found in inverters. And they can just fall off. And worse still, they can touch the case or they can touch other components. And anyway, if you have an open circuit on the output stage between these 2 vertical terminals here, the ones I'm pointing at, that's a cause for concern. Again, don't try to operate the inverter. It's going to need to be opened up and repaired. And another trick is you can actually check both outlets to see if both have an open circuit. So If you stick the probes in here and you get the same exact reading, you should get the same exact reading, then there's probably nothing wrong. The outlets are fine. If you get an open circuit on one and not the other, then you're going to need to open this inverter and find out what went wrong, because probably one of these outlets failed and possibly a wire came loose or something like that. It's just something to keep in mind. So short circuit, open circuit, those are failure conditions. If you measure the inverter on the output side and you get a pretty decent reading in the hundreds of ohms, you don't have to worry about it. It's not shorted out. It's probably just fine. That, however, doesn't guarantee that the inverter is going to work perfectly. It may not work at all. But there's a chance that if you find these conditions on the input and output, you already have enough information to make your decision whether to try to repair the inverter, whether to open it, or whether to just throw it away. Now, if you'll notice, I never actually opened the inverter at all. I didn't try to take any screws out or open it or do anything. All I did was look at the inverter from the outside to see if it was in good condition or not. If you don't feel comfortable opening an inverter, you can still check them or diagnose them to a degree by using a multimeter, and it only takes a few minutes. You might even save some money by having this knowledge and having access to this information. The intent of this video is not to get too down in the weeds and too bogged down in heavy electronics. I'm not going to open the inverter and show you every single component on the inside, but just some basic checks that you can learn to get started in that direction. You can always add more knowledge later. Now here's a common one. What if you have an e-bike battery pack, such as the one shown here? As you can tell, this one has had better times. It's basically torn open. What if you have a battery pack like this and you're not really sure what's wrong with it or what happened, and you want to sort of start working on it, kind of diagnose it and find out what went wrong? Let's just pretend that this battery isn't really charging and it's not really running a load, and you're not really sure what's going on with it, and you just want to do some basic checks to see what's going on. Let's go ahead and try that. To fill in the background, this is a 16S or 16 cell LiFePO4 or lithium iron phosphate battery pack, which some time ago stopped working. I noticed that it did not really put out any voltage, and when it did, it was very weak and it would turn off, and I couldn't really charge it, and so I knew something had gone wrong with it. I always suspect these circuit boards that are on the top, known as a BMS sometimes, or a battery protection circuit. I'm not a huge fan of them, to be honest, and I'm not really a big user of them. This is a store-bought battery. I did not build this myself, and so it came with this so-called BMS already in it, and I actually really suspect that it is the reason why this battery pack stopped working. Anyhow, let's go ahead and do some basic steps to see what's going on with this thing and whether it can be fixed. In order to troubleshoot a battery like this, the first thing I would do is switch the voltmeter to voltage. So we'll go ahead and go to the voltage range, DC. When troubleshooting a battery like this, it's a relatively large battery, and if you make a mistake and probe the wrong place, it can really cause a lot of problems. So I always put the shrouds on whenever I can. Now, at the top of the battery, there's this kind of ribbon cable here with all these connections. These are going to all the cells, and these are all the monitoring and probably balance wires used by this BMS. Then you have some other wires. You have a big black wire coming out here. This is another black wire coming out. This is the discharge lead. And then here's a red wire, and this goes directly to the battery, and that's the other discharge lead. Clearly, this particular battery here is not actually using the positive lead. It's not actually connected. Only the negative lead comes in here, and that is because this BMS uses the negative side of the circuit to turn the protection on and off, so that's actually quite normal to see. Therefore, this positive wire here most likely appears to be soldered directly to the battery. And that's the same for the charging lead, which is right here. And then you have your other charging lead, which is negative, and that goes to the BMS. So the negative side is doing the switching, which is actually very common, and the positive side is going literally straight to the battery terminals. There doesn't appear to be any fuse or anything on that side. And that's relatively standard. I see that all the time. The first thing I want to do is I want to probe the BMS output to see if there's any voltage. So the first thing I'm going to do is I'm going to take my voltmeter probes, and I'm going to probe the positive, and then I'm going to probe the negative output. And you can see I'm only getting 22 point something volts. Notice now, it's hard to keep the probe on there without slipping off, but notice that the voltage is kind of falling. Why is that? Well, I'm going to tell you why that is. The answer is that this battery has it's shut off. And what's happened is the BMS is actually turned off, and what you're seeing when you probe the output on the battery, it's very deceptive because it looks like the battery's dead and it's kind of slowly losing voltage. What's actually happening is there's a very high resistance connection between the voltmeter and the battery through the BMS. And that voltage there is really not accurate. And the reason why it's going downhill like that is because basically the MOSFETs, which are in this BMS, have probably switched off and they're actually interfering with the reading on the battery. So how do I get around that? The answer is you want to bypass the BMS. What I'm going to do now is I'm going to bring my probe around to the other side of the BMS, and that's right there. You can see that wire there. And that is actually the negative feed wire coming from the main battery pack. So let's go ahead and measure that side next. And you can see I'm getting a high voltage warning. It probably would zap me a little bit, maybe under some conditions. But as you can clearly see, this battery is reading at about 49.5 volts. However, that's actually pretty low. It really should be for a 16-cell lithium iron phosphate that hasn't been abused and run flat. It ought to be up in the 50 volt range, maybe 51 volts. And as you can see, it's clearly not. It's 49.5 volts. Now that doesn't tell me a whole lot of anything. It's useful information to know, but it still isn't going to help me solve the problem. So the next thing I'm going to do is I need to actually measure the individual cells. And let me tell you, that's tedious. This is a 16-cell battery. And on this side of the BMS, you can actually see there's a whole bunch of connections. Now you'll see that there's a black one here, and there's a whole bunch of white ones, and then a red one. Black is actually the ground, or the main negative of the battery pack. All these white ones are all the junctions in between all the different cells that are in series, and red is your final positive terminal. If you're very careful, you can actually probe these connections and try to find which cell is low. So let's go ahead and give that a try. Now, if one of the cells is low, it should be pretty obvious. You're looking for a lithium iron phosphate, you want to see about 3 volts. So let's go ahead and probe these and see what's going on. Now be careful because it's very easy to short these out. I'm going to go ahead and start probing from this side. That's fine, 3.3 volts. And notice how I move my probes over. 3.3 volts. Yep, 3.3 volts. 3.3 volts again. And on this cell, I'm actually getting nothing. Let's go ahead and try this cell again. Maybe I'm touching the wrong connection. No, unfortunately, this cell is probably dead. I'm getting pretty much nothing on there. About 400 millivolts. That's not very much at all. Basically, that's dead. Unfortunately, that cell appears to have shorted itself out, or it's failed in some way. And the next cell over is about 3 volts again. And I'm not going to bore you with checking all of them, but basically this is how you would do it. You would go along to each of these connections here and make sure all the cells are around 3 volts and that there's nothing out of the ordinary. But as you can see, I already found a bad cell. It could either be disconnected or something's gone wrong. To just quickly summarize what I've done here, if I have a battery that's acting like I just described, where it does not really want to charge, it doesn't really run anything, and it keeps switching off, or it shows a very low voltage, and it won't accept a charge, it won't run anything, and I can't do anything with it, one of the first things you want to do is get inside the battery and check both the main pack voltage, positive and negative, and then unfortunately you have to go through and check every single cell to see if maybe one of them has failed or is overcharged or whatever. And you can see that's quite a tedious process. Once you determine, for example, in this case, if there is a bad cell, the next step is to take the BMS off, and of course you'll have to access the top of the battery or wherever the terminals are, and you're going to have to find that bad cell. In this case, you can see I've already been in this battery and I've already found the bad cell, and it's one of these here. So this battery would have to be repaired. That means replacing one of the cells, and let's just say it's not an easy job, but with a battery that costs quite a bit of money, as this one did, the cell might cost you $50 to replace, maybe $30, and it might actually be worth it. Otherwise, you could recycle the rest of these lithium iron phosphate cells and use them for something else. There's still 15 good ones in here. Maybe you can make a 12-volt battery or something like that. Regardless, once you do these basic checks of the battery plus and minus, and check the output of the BMS as well as the input, and then each individual cell, you have some basic information in just a few minutes on what to do with that battery pack, whether it's to replace the cell or to just throw it away or maybe recycle it or take it apart or whatever you want to do with it. Anyway, when you open up batteries like this, you're going to find probably a lot of interesting things, and I mean that in quotes. Bad soldering work and who knows what else. But a digital multimeter like the Gochifix multimeter here can give you a lot of information in just a few minutes and may actually save you some money. Who knows, you might be able to fix an expensive battery instead of just throwing it away. A quick summary of my thoughts on the Gochifix 3-in-1 multimeter shown in this video. I've been using this multimeter for quite a while now, and I must say, compared to other multimeters that just works like a multimeter should, it has the smart functionality there if you want it. Otherwise, it acts very much like any digital multimeter I've ever seen. For somebody who just wants a nice digital multimeter with a clean display and a fast update rate, the Gochifix will do the job. Many solar power enthusiasts might be interested in trying or using an oscilloscope but aren't willing to pay for the full instrument. The fact that the Gochifix 3-in-1 meter includes an oscilloscope built into it is actually really attractive, and I found the oscilloscope mode to be very easy to use, and I was not disappointed in the slightest bit. Keep in mind that I don't get paid for selling this meter, and I'm just giving you my honest opinion and theories. I think that it's well designed and it meets its target audience. Considering the price of this multimeter, I don't think they're asking too much for the level of functionality and quality that is included. This multimeter will actually be used well into the future, probably on my workbench at different times and also on the go, which is the best compliment it could get. If you'd like to pick one of these meters up, I've placed the link in the description to the manufacturer's website. I hope this video helped you out. Thanks for watching, and I'll see you next time.